Hello students, welcome to Pharmaceutical Concepts. Let us solve two questions from the previous question papers of GPAT. So the first question is increase in the extent of conjugation of a double bonded system results in what? Okay, so let us first see what are these. We know that when any molecule, okay, when any molecule absorbs UV radiations, hmm, uh, UV radiations, as I told you earlier, these are the radiations from the electromagnetic spectrum, okay, and they possess some energy with them. So when these UV radiations are bombarded on any molecule, this molecule means nothing but a structure should come in front of our eyes. Okay, so these structures which has carbon, which has hydrogen, which has number of other elements, which has number of other bonds, it has number of electrons. Okay, so the energy of the UV radiations will be absorbed by this particular molecule. After absorbing the energy, the valence electrons of the system, valence electrons of the molecule, okay, these valence electrons, they show transitions from the ground state. Okay, so from ground state they move to the excited state. So there are different types of transitions based on the different type of electron. For example, there is sigma sigma star transition, there is pi pi star transition, there is n sigma star transition, and there is n pi star transition. So what happens whenever there is increase in conjugation? Suppose I have this particular system with me, I have this particular molecule. So in this molecule has a certain absorption energy, it will absorb certain energy from the UV radiations. But if I add one more unit, suppose I have added here one more carbon, and if there is one more double bond here, so what is the effect of this increased conjugation? So such increased conjugations, or if you substitute here any alkyl groups, okay, so all these things, they affect these transitions will be affected. So based on this, what happens, um, there are these type of shifts. So bathochromic shift means, for example, any particular molecule is giving UV spectrum like this, okay, where this is the lambda max of that particular molecule. Now in that molecule, if I add a certain functional group, and because of that functional group, suppose I have this particular molecule. Now here this molecule has certain lambda max, but now if I am adding some functional group to it, so the altogether the structure of the molecule has been changed. So definitely the lambda max will also change, means its UV pattern, UV spectrum pattern is also changed. So that molecule, if its lambda max now changes to the higher value, okay, then that is called as bathochromic shift. Okay, and who was responsible for this bathochromic shift? This particular functional group, right? So this may happen, suppose this is the original lambda max of the compound. It may happen that because of the addition of certain functional group, if I'm adding certain X functional group over here, so because of this X, the now the molecule is showing absorbance here, so its lambda max is reduced. Okay, so that is called as hypsochromic shift. This hypsochromic shift is also called as blue shift, and bathochromic shift is also called as red shift. Okay, let us see what is this hyperchromic and hypochromic shift. If this is the original molecule giving me the absorbance, or this is the lambda max of the original molecule, if by addition of certain chromophore, or by deletion of certain chromophore, presence of any substituent on that particular molecule, if the absorbance is increased, means the lambda max is same, Okay, but the absorbance, see, absorbance is increased, lambda max remains same, but the absorbance is increased, then that is called as hyperchromic shift. Okay, or if in any case the absorbance is reduced, suppose by any substituent, lambda max remains the same, but the absorbance is reduced here, then that is called as hypochromic shift. So tell me what should be the answer now. I repeat the question. Increase in the extent of conjugation of a double bonded system results in. So let me show you the answer. Answer is bathochromic shift. So here our next question is, a monochromator is not used in which of the following instrument? What do we mean by monochromator first? Monochromator is the part of the instrument which selects a wavelength. Okay, it selects a single wavelength from a polychromatic beam. Okay, polychromatic beam means what? Means inside the instrument we have a source of light. So from this bulb we are getting all type of radiations. Okay, suppose if we consider a white light. Okay, so this white light is made up of what? Vibgyor, right? So white light is made up of all the different types of wavelengths. These all have different wavelengths with them. This is the wavelength, then wavelength is increasing, then increasing more and more. So all these, this white light is a mixture of all these wavelengths. Now from these wavelengths, suppose for my experiment I want only single wavelength. For example, from here I want wavelength of 423 nanometers. Okay, then this monochromator I will keep here. I will give the instruction to the instrument to select 423 nanometer, and from all this 400 to 800 nanometers, from this range the monochromator will allow only 423 nanometer to pass out. Okay, and that will then pass through my sample. Okay, so such monochromators are available, or they are present in UV spectrometer, they are present in IR spectrometer, they are present in spectrofluorimeter also, but in FTIR, okay, in FTIR what happens, that is the Fourier transform, okay, IR spectrometer. So in FTIR, instead of that we have drive mechanism, we have a splitter beam splitter, and then we have a transducer. Okay, so in FTIR this monochromator is not present. So here our answer is FTIR spectrometer. It doesn't have monochromator in it. Thank you very much for watching, and stay tuned with me for the more questions from the old question papers of GPAT. All the best.